Good evening, everyone. On the behalf of Department of Mathematics, Wilson College Autonomous Mumbai, I welcome you all in the today's session. Our today's guest is Dr. Anand Chitrao, sir. He is an postdoctoral researcher at Department of Mathematical Sciences, Ulsan National Institute of Science and Technology, South Korea. He will deal with the topic of group theory today. Over to you, sir.
Thank you. Um, so let's begin today's lecture with a few doubts that were asked before the start of this lecture. So, yeah, please ask.
Yes, sir. I am asking about
Sure.
the yes, sir.
Hmm.
Are you listening?
Yeah,
Yeah.
I can hear
Yes.
you.
Yes, sir. Sir, I am asking about we are all acquainted with the notion of dihedral group, and
Hmm.
which is generated by the composition of rotation and reflection togetherly, and they are obeying certain condition. Uh, but I am doubtful, sir. I have to remember this particular condition during problem solving. But are these condition are how are these condition are came into existence such that we can abstractly extended it for the nth order dihedral group, but it is
Yeah.
yeah.
Uh, so you are asking about the definition of the dihedral group and why is it so, right?
Yeah, yes, sir, because it elements are conveying certain properties which is not commutative also, but they are related to the rotation, composing reflection in the certain order. But how they are coming to existence in such a well-behaved manner?
Yeah. So this will show up later in today's talk in the context of semi-direct products. But let me first tell you some things about the dihedral group. So can you tell me the presentation for the dihedral group? So Dn consists of,
Set of rotation denoted by R,
yeah, so
and
it's
reflection which is denoted by
generated
S.
by, hmm,
And order of R is a cyclic group, so cyclic subgroup. It is a order of n. Order of R is equal to n, and order of S is equal to 2.
yeah,
And it following certain conditions. Suppose R compose S, its
hmm,
square is equal to identity.
yes. But let's write that in this format, that S R S inverse
Yes, yes.
equals R inverse.
It can be manipulated in this form. R composes
Yes,
square.
it can be, but
Yes,
this is a nice way to write it, is what I'm telling you.
yes, sir.
So what this tells you is, um, first of all, every element of Dn can be written as some power of R times some power of S. Okay,
Yes, sir.
that's because Dn is generated by R and S subject to this relation. Is that clear? So if you didn't know some relation like this, you won't be able to write every element in this form. Okay, but just believe me for the time being that thanks to this relation, you can write every element in the form R power I, S power J. This can be proved using first principles, also counting. But okay, now given two such elements, how do you multiply them? Suppose you take R power I, S power J, R power I prime, S power J prime. How do you multiply them? So this
Yes,
tells you how to multiply them. Whenever S is on the left of R, you can bring it across at the cost of changing the sign of the exponent of R. That's the point. So I think this relation is beautiful because of this reason. it tells you how to multiply things. If you just had r times s whole square equals identity, you wouldn't know how to multiply this, right? For instance, what happens when I is 0 and whatnot. So yeah, I think this way of writing that is nicer. Next, you were asking about some physical interpretation of this group, right?
Yes, sir. At least intuitively, how
Yeah,
it is work.
right. So the physical interpretation of this group is in terms of symmetries of certain polygons. So what one does is one looks at R2, the plane, and one looks at all the linear transformations of that plane. Sorry, I shouldn't say linear transformation, linear isometries of the plane
Isometries where distances are preserved.
are preserved. And one chooses the regular n-gon and then looks for all those isometries which take the n-gon to itself. Okay, this is also the set of all or the group of all isometries. I'll say linear isometries of R2 fixing a regular n-gon. Okay, uh, so this means D3 would be linear isometries of R2 fixing an equilateral triangle, right? Then D4 would be linear isometries fixing a square, and so on and so forth. Now, you see, this R, suppose you are in the case of D3. Suppose you are in the case of D3, then R is supposed to be rotations. R is supposed to be rotation of 120 degrees. Or rotation by, sorry. Rotation by 120 degrees. Is that clear? If you have an equilateral triangle and you rotate the plane by 120 degrees, this point will go to this point, this point will go to this point, and this point goes to this point. Is this much clear?
Yes, sir.
Yes, sir.
Yeah. So this is the physical interpretation of the element R. Next, S is supposed to be a reflection. So first let me denote this. So this is what R does. Now, what S does is, S is reflection about the line passing through an altitude. Okay, what does that mean? If you have this triangle, equilateral triangle, you take an altitude. Sorry, this is off. The scale is bad. So in an equilateral triangle, the altitude is also the perpendicular bisection and whatnot. So you take the line passing through this altitude and reflect along this line. So this point is taken to itself and these points are exchanged. That's what S does. Is this much clear?
Yes, sir.
Yes, sir. Yes, sir.
Okay. Now I've told you what R and S are. Now let's verify some things. First verification is that the order of R is 3. So is it clear why the order of R is 3?
Yes, yes, sir. Because after 360 degree, it would be same as original.
Yes. So if you start with this point, it goes to this point, goes to this point, goes to this point. So you can see it at the level of these points. But if you think of it as rotation by 120 degrees, then as you said, rotation by 360 degrees is nothing. Next, can you see that the order of S is 2?
Yes, sir.
Yeah, because double reflection is doing nothing. So that much is clear. Now what about this mysterious relation? That if you conjugate R by S, you get R inverse. So let's do this exercise. Suppose you have this triangle. Let's number the vertices by 1, 2, 3 this way, anti-clockwise. You have to compute. So check S R S inverse equals R inverse. Okay. So first apply S inverse. So what will S inverse do? It will send this triangle to itself. 1 will stay fixed. 2 and 3 will get exchanged, right?
Yes, sir.
Next, what will R do?
So rotation by
R will
120.
send, yeah, R will send 1 to this thing. So this will be the new 1, this will be the new 3, this will be the new 2. And finally,
Yes,
what
sir.
does S do? It permutes these two vertices, right? It exchanges these two. So 3, 1, and 2. Now you see what happened from here to here in total. Can you see it's just rotation by 240 degrees?
Yes, sir.
Yes, sir.
Yeah. Instead of 1 going to 2, 1 went to 3. Instead of 2 going to 3, 2 went to 1. And
1.
instead of 3 going to 1, it went to 2.
And
So
it
this
is
is the same as R
R
inverse.
inverse.
So you can see that you got R inverse if you conjugated R by S. So that's the physical interpretation of this equation. Next, you also said that there is one more relation which says RS square equals identity, right?
Yes, sir.
Yeah, so let's look at the physical interpretation of this. What does this say? This says that the order of RS is 2.
Yes.
Okay, this
Uh,
says that the order of RS is 2, obviously because RS
any
is not identity.
yes, sir.
Yeah, so now um, what is it looking like? What is RS supposed to be? Is it a rotation? Is it a reflection?
It is a reflection.
Yeah, so let's see what happens. So if you try to compute RS, so 1, 2, 3, S sends 1, 2, 3 to 1, 3, 2, and then when you apply R, you get 2, 1, 3, right?
Yes, sir.
Yes, sir.
So in total, RS results in fixing 3 but exchanging 1 and 2.
It is a reflection.
Yes, about the line passing through the altitude starting at 3. Okay, what is RS supposed to be? Reflection along the altitude starting at 3. Can you see that?
Yes, sir.
Yes, sir.
Yeah. In this way, can you guess what is R square S supposed to be? What's the interpretation of R square S?
It is R only.
R square S is R. Tell me the order of R square S. Let's do this. Is R square S equal to identity? No, right?
No, sir.
because when you multiply on the left by r, that would say s will be equal to r. So this is not identity. What about its square? R square s times r square s. What's this?
Identity.
Why? So can you tell me how did you do that?
Yes, just sir, if we separate R and R, first
S
R,
R square S equal
uh,
to
Yeah,
R,
just this much is what? Yeah, can you repeat? This much is just
R square.
s r square s is supposed to be r, right?
Yes, sir.
Let's do that slowly. So s r square s, how can you write it? So this is the same as s r r s, right? So now you write this as r square s r s inverse s r, and this s can also be thought of as an s inverse because it's of order 2. Now SRS inverse is R inverse, SRS inverse is again R inverse. So this is R square times R power minus 2, which is identity. So this says that the order of R square S is 2. So what is it looking like? It's looking
Uh,
like a reflection, right?
yes, sir.
Yeah, R square S is looking like a reflection. And you can check that it's the reflection about the line passing through the altitude starting from 2. R square L S will fix 2, but it will permute 1 and 3. Okay? So this is the physical interpretation of the group DN. Uh, Anything else regarding this?
Sir, if you change the direction of rotation, then it can affect or not.
No, that's the beauty. This is an abstract result that DN is a group and it's generated abstractly by two elements R and S, R of order n and S of order 2, satisfying this relation. So now to answer your question regarding the direction, is this DN also generated by R inverse and S? That's your question, right? Satisfying the same relations?
Yes, sir.
Because if R is supposed to be rotation in the anti-clockwise direction, R inverse will be rotation in the clockwise direction. So now it's clear that if R and S generate Dn, then R inverse and S generate Dn, right? What's the order of R inverse? If the order of R is n, what's the order of R inverse?
N.
N.
Yes, n again. S doesn't change, so S square is identity. Now what about S, R inverse, S inverse?
R.
R, sir.
Yeah, why? So one can check that this is the same as S, R, S inverse, whole inverse. You can try and multiply these two, you get identity. And what is S, R, S inverse? It's R inverse. And R inverse inverse will be R. So this is looking similar, right?
Yes,
So it doesn't matter what R is. R can be rotation in either direction by 360 divided by n degrees. Okay, or pi by 2 divided by n radians. Whatever.
Yes, sir. Okay, sir.
Anything else?
no,
No, sir. And sir, this result S R S inverse is equal to R inverse. It means that if we conjugate any element of the group with S, then it
Mhm.
always equal to the inverse of that element.
Yeah, that's a corollary. It's not true. It may not be true for an arbitrary group though. Okay. It just so happens to be true for this group.
Okay, sir.
Yeah,
Sir, can you show the upper slide so that I can take the screenshot?
sure. Which upper slide?
So from starting to up to end.
Uh, yeah, I'm writing vertically, and this may not fit in a single page. But if you want, I can flash some things over here. So did you take a screenshot of this?
Yes, sir.
Yeah, okay. Then the next thing, take a screenshot of this. I think that's it.
Yes, sir.
Yeah. And there was a second question, right? Before the start of the lecture. One question was regarding DN and the other one I forgot.
The class equation.
Right, the class equation. Yeah. So you wanted me to explain the class equation again, right?
Yes, sir.
Yeah. So let G be a finite group. Now, given any X in G, we can define a subgroup of G denoted by CG of X. Okay. This is supposed to be centralizer in G of the element X. This is defined to be the set of all little g in capital G such that little g commutes with X. You can write it in this way. Gxg inverse equals X. Okay. One can check that this is a subgroup of G. Is this much clear?
Yes, sir.
Okay. Then this is a subgroup of G. I'll repeat it even though I said it here. So since G is a finite group, the index of this in G makes sense. So you look at the number denoted by G colon CGX, which is equal to the cardinality of G, the order of G, divided by the cardinality of CGX. Okay. This is called the index of a subgroup inside the big group. So or what the class equation says is, if you look at the order of G, that is the same as summing up all these indices. G colon CGX, not over all elements X in G, but these X's are representatives, one each one coming from a different conjugacy class. This is a sum over X. Okay. So yesterday the day before yesterday we saw that there are certain interesting subsets of G called as conjugacy classes. So they comprise of all those elements which are conjugate to a given fixed element X. Okay. So turns out that G is a disjoint union of those conjugacy classes. One can check some equivalence relation over there. The equivalence relation being conjugation, but you can see that G is a disjoint union of conjugacy classes. Now, the size of one particular conjugacy class, let's say the conjugacy class of X, is equal to this index. One can show that. Just this much, this can be shown. This equals the size of the conjugacy class of X in G. Is this much clear?
Yes, sir.
Yeah. So what we did is started with G, wrote that as a disjoint union of all conjugacy classes. Therefore, the order of G is equal to the sum of the cardinalities of all the conjugacy classes, right? Now, we just wrote the sizes of the conjugacy classes in this way as index of a certain subgroup of G. So this is the class equation. Now it has a different avatar. This can also be written as, when some people write this as ZG, the cardinality, plus the sum ranging over the same x's, x representing all distinct conjugacy classes in G, but x not in the center. Okay? This is a different form of writing the same equation. And this has some interesting corollaries, like the fact that center of a P group is non-trivial and whatnot. So does this clear your doubt?
Yes, sir.
Yeah. Those who know a bit of advanced group theory, and those in particular, those who know group actions, the point over here is we are looking at the action of G on itself by conjugation, and this is essentially the orbit stabilizer theorem. Okay. Are
Yes,
there any
sir.
more doubts? If not, let's begin with today's lecture. So I would like to tell you something about homomorphisms. So we saw in the previous lectures the phrase isomorphisms, right? So what is an isomorphism? Isomorphism is a way of saying that the two groups are the same. And if we relax the definition of an isomorphism, we get the definition of a homomorphism. So what is a homomorphism? A function f from a group G to a different group G prime is a homomorphism if f of G1 G2 equals fg1 fg2 for all G1 comma G2 in capital G. Is this clear?
Yes, sir.
What this means is this is a function from G to G prime which respects the group structures. This is a phrase commonly used in mathematics, which means it takes a product in the first group to the corresponding product in the second group. Next, let me first give you some definitions and then we'll look at the examples. So associated with a homomorphism, there are two subgroups. So can somebody tell me what those are? Just a guess. If you know. Okay. So those are kernel and image. So start with an f from G to G prime, then you can define what is called as the kernel of f, and this is the set of all little g in capital G such that f of g equals E. Okay, where this is the identity of G prime. In other words, there is also f inverse of EG prime. Is the definition clear?
Yes, sir.
One can check that there is a subgroup, but more importantly, this is a normal subgroup of G. And essentially, every normal subgroup of G arises as ker F for some F. So that's why these are the most important examples of normal subgroups. Then image F. Image F is all G prime in capital G prime such that there exists a little g in capital G such that G prime equals f of G. Okay. This is also denoted by f of capital G and is just a subgroup of G prime. It may not be a normal subgroup. Okay. Are these two definitions clear?
Yes,
Yes,
sir.
sir.
Yes, sir.
Great. So then we say that F is an isomorphism onto G prime if ker F is capital G and MF is capital G prime. Injectivity, surjectivity. So what's an isomorphism? It's a homomorphism that is bijective. Okay.
Sir,
If,
kernel should be only identity set, na?
oh, sorry. Thank you for pointing that out. Kernel should just be identity. Is that clear? Sorry for that mistake. If there is an isomorphism F from G to G prime, then we denote or we say G is isomorphic to G prime. We denote it using this symbol. I'm stressing on this because these are really important things. Isomorphisms. So what are some of the examples? Let's start with some easy cyclic groups. Can somebody tell me examples of homomorphisms between cyclic groups? Yeah, so you can start with Z.
Z plus Z plus, and get that function as a k of x, where k is
Yeah,
integer.
okay. So you start with Z and you want to land inside Z. And it's enough to just say what happens to a generator. Okay. So where do you want to send 1 to? You want it to be sent to K, right? For some K in Z. So this is a homomorphism. When is this an isomorphism?
So when k equal to 1, if 1 goes to 1.
1 and
Yeah,
minus 1.
right. So there are two values of K for which this becomes an isomorphism. One is +1, the other one is -1. Next, how about Z going to Zn? Are there homomorphisms from Z to Zn? You can do the same. Start with 1, send it to k bar for any k that you want. Okay? For which values of k is this an isomorphism?
So K is equal to
For GCD of K and N equal to 1.
Can this be an isomorphism? This is a infinite set and this is a finite set, right?
Oh,
yes,
yes.
sir.
No
They
isomorphism.
cannot be isomorphism.
Yeah.
Both set needs to be finite.
Yes. I mean, both needs to have the same cardinality. Never an isomorphism. How about homomorphisms from Zn to Z?
No, sir.
What no?
So because Z is a finite group, then isomorphic to finite group.
No, I'm not asking for isomorphisms, I'm asking for homomorphisms.
We can send 1 to some K.
You can send 1 bar to k. So let's see, for what value of k will this be a homomorphism? Okay, you know that if you add 1 n times on the left, you get 0, the group identity.
Yes,
Okay,
sir.
Yes.
so f of n times 1 bar equals f of 0 bar, and one can check using the definition of homomorphisms that f of identity is always the identity. What's the identity in Z?
0.
0.
0.
0. So you see that f of n times 1 bar equals 0. But you can inductively prove that. So you see what happens over here. You can write this as f of n minus 1 times 1 bar plus 1 bar. So this can be written as f of n minus 1 times 1 bar plus f of 1 bar by the definition of homomorphisms. So if you keep on doing this, you can see that this is just n times f of 1 bar. Can you see that?
Yes, sir.
Yes. Because you could pull out an f of 1 at the cost of decrementing this n. So you can do this. You can see you can do this n minus 1 times, but then you'll be left with 1 over here. So n times f of 1 bar. So all of this chain says that n times f of 1 bar is 0. But f of 1 bar is an integer, right? F of 1 bar is an integer. So n times an integer equals 0. What does that say?
The integer must be 0.
Right, the integer must be 0. f of 1 bar equals 0. So this is a homomorphism if k equals 0. But you can say something more, if and only if k equals 0. Okay? This is called a trivial homomorphism. There always exists a homomorphism between any two groups in this world, um, and that homomorphism is a trivial homomorphism. Send the entire group to the identity. Okay? Yeah. So now some non-abelian examples. So give me a homomorphism from Zn to Sn. Where should I send 1 bar to?
Identity permutation.
Yes, the identity. That's good. Now what about an injective homomorphism?
So n equal to 2 4s2.
Okay. So you want to give an example for n equals to 2. So Z2 to S2, you're sending 1 bar to, what did you say?
We can send 1 to 1 comma 2.
Yes, to the permutation 1, 2. So try to generalize this and tell me the answer over here.
Any n cycle.
Right. So you can just fix a cycle. So 1, 2, dot, 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 n. This is an injective homomorphism. How about an isomorphism between these two?
No
Do the same as
isomorphism.
what we did here.
Yes, sir. There will be no isomorphism
Why?
because one is abelian and another one is non-abelian.
Yeah. So Zn is abelian and Sn is non-abelian, we saw. If there is an isomorphism, then we are saying these groups are the same, right? So um, an abelian group cannot be the same as a non-abelian group.
Sir, for n2 it is here both are abelian.
Exactly. Yeah. So I was talking about general n. Nice catch. So
I
there are
think
some
n greater equal to 3 for we cannot get
Yes.
isomorphism.
Yes. 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 So I'll write Zn not isomorphic to Sn for n greater than or equal to 3. You can also see from their cardinalities. What's the cardinality of Zn? What's the order of
N.
Zn?
And
N. And what's the order of Sn?
n
n
factorial.
factorial.
n
N
factorial.
factorial. So can n factorial be equal to n?
No,
No.
sir.
Yeah, only for some small values. Next, tell me a homomorphism from Z2 to Z6. And now let's restrict to non-trivial homomorphisms. Those are interesting. So where do you send 1 bar to?
3.
So you do the same. You first check what's the order of one bar. What's the order of one bar over here?
2.
2.
2.
2.
2.
So you have to send it to some element whose square is 0, right? That's what we got from this calculation. We note over here, we saw that the order of 1 is n. And then we concluded that n kills f of 1. So do the same over here. Order of 1 bar is 2. Therefore, 2 will kill f of 1 bar. Which means you have to look for elements in Z6 whose order is divisible, order divides 2. So how many of those are there?
2.
3 bar.
Yeah, for x such that order of x divides 2. And the answer is 2. What are those?
One is identity element and another one is 3.
Yes. So one is 0 bar and the other one is 3 bar. Okay. So remember this fact that image of an element has order dividing the order of the element that you started with. So if f from G to G prime is a homomorphism, then for all little g in capital G, order of f of G divides the order of G. This is a fact. This small lemma you can check. Order always goes down. Next, this set of all homomorphisms between two groups is denoted by hom G, G prime. This is a set of all f from G to G prime. Now, I'll just tell you one result. You can try to prove it yourself. The number of homomorphisms between two cyclic groups Zm and Zn is the GCD of M and N. Okay, there's an important fact. This shows up a lot in JAM. Next, I'll tell you some isomorphism theorems. So, first, a fact, take this as a black box. Let G be a group and let H be a normal subgroup. Okay? Then there exists a group denoted by G slash H. This is called G mod H, such that some properties are true. Okay?
Sir, it is not isn't a factor group.
Yes, this is called the factor group or the quotient group. Okay?
Yes.
such that there is a surjection G to G mod H satisfying a few properties which I won't write over here. Okay, so when without these properties, it looks like there is no content to this fact, but all that it says is if you start with a group G and if you take a normal subgroup H, then you can make a different group G mod H. Now let me just tell you what G mod H is. So G mod H as a set is equal to these symbols, little g, capital H. Okay, such that little g is in capital G. So these are what are called as cosets, cosets of H in G. Then you multiply these in the following way. So if you take a coset GH, G prime H, you multiply these in the obvious way, G times G prime H. Okay. All that you need to know is G mod H consists of elements like this, symbols G times H. The way of multiplying any two such elements is this, and equality. I have to tell you equality. GH equals G prime H if G inverse G prime belongs to the subgroup H. From this data, you can determine what G mod H is. Okay. I'm just giving you a crash course on factor groups over here, but you can read more about them in many books. But yeah, I think this much is enough. Then I'll give you a few isomorphism theorems. The first isomorphism theorem, the second isomorphism theorem, and the third isomorphism theorem. Let F from G to G prime be a group homomorphism. Then, as you saw above, kernel F is a normal subgroup. So you can ask what G mod kernel F is. Then G mod kernel F turns out to be isomorphic to the image of F. This is the first theorem. Okay. Is the content of this theorem clear?
Yes, sir.
If you start with a homomorphism from G to G prime, then I told you that kernel F is a normal subgroup. So you can construct G mod kernel F. There is a different group. This thing on the domain side is somehow the same as the image which is on the codomain side. Then the second one, S is a subgroup of G. Sorry. Let S be a subgroup of G and N be a normal subgroup of G. Then Sn turns out to be a subgroup of G. This equals the set of all little s times n inside G such that little s is in capital S, little s n is in capital N. And n is a normal subgroup of a big group, therefore n is a normal subgroup of anything smaller. So you can ask what Sn mod n is. this turns out to be isomorphic to S mod S intersection N. Okay? Is this clear?
Yes,
Start
sir.
with any arbitrary subgroup and take a normal subgroup. Then construct this subset, which is a set of all products. Okay? This turns out to be on a subgroup of G, and Sn mod n is isomorphic to S mod S intersection n. These are really crucial theorems. Next, take a chain of subgroups n contained in n prime, contained in G, with n being normal in G, n prime also being normal in G. Then one can look at G mod n, as you saw, and one can look at n prime mod n. Is this clear? N prime is normal in G, and n is a subgroup containing n prime. Sorry, n prime is a subgroup. I mixed it up, sorry. N is normal in G, and n prime is a subgroup of G containing n. Therefore, n is also normal in n prime. So you can construct this factor group. Turns out there is also normal inside G mod n, and G mod n whole mod n prime mod n. This turns out to be isomorphic to G mod n prime. So there is some sort of a cancellation law. So if these were rational numbers, then you could cancel n, right?
Yes.
So yeah. So these are some of the most important theorems in group theory. So never forget these. And try to look at their structure. You'll see theorems like this everywhere in mathematics, in every branch of mathematics. Next, maybe I'll start with semi-direct products. I find these interesting because these give you a way to cook up new groups, starting with smaller groups. Okay. So let's start. Let G be a group. Then ought G. This is the set of all isomorphisms from G to G prime, sorry, G to G. This is a set, but under composition of functions, this becomes a group. Okay. Under composition of functions, this becomes a group. Can everybody see that? Composition of
Because it is
isomorphisms.
a
Yeah,
bijective function, composition of bijective function, bijective, all are the
right.
whole square.
Exactly. So this forms a group under the composition operation. So you just checked the closure property. What about the identity?
It is trivial homomorphism, isomorphism.
Yeah, the identity, not the trivial one. let's call it the trivial one sends everything to just the group identity, right?
Oh, sorry,
That's
sorry.
no good. Yeah. So you need the identity homomorphism. Send G to itself. Send little g to itself. Then what's the inverse of an isomorphism? It's just the inverse as the function, right? So that shows that odd G forms a group under composition of functions. So this is important. Now, suppose H and N are groups and we have a homomorphism theta from H to ought N. So we have just seen homomorphisms from H to N, right? There's one level higher. This is a given homomorphism from H to the group of automorphisms of N. Okay? Then we can construct a group denoted by N. Let me see the order. Yeah, N. Then this angled alpha and H as follows. Okay, so elements of that group are ordered pairs N comma H such that N is in capital N, H is in capital H. And I have to tell you the group operation. So suppose you are given N, let's not complicate the notation, N, H and N prime, H prime. I have to tell you how to multiply these. So the idea over here is you try to multiply N and N prime together and some twist of H and H prime together. So what is this? I'll just write the group operation N1 times you apply this theta to, sorry, not N1, N times you apply the theta to H. That will give you an automorphism of N. So you can apply that further to N prime. Okay? Theta of H is an automorphism of N. So it's a function from N to N. Apply that to N prime. Multiply these two together. And in the second coordinate, just multiply H and H prime together. Is this group operation clear?
So can you repeat the last one?
Yeah. So you start with N comma H, that's element 1. You take N prime H prime, that's element 2. So what you do is you multiply N with a twist of N prime. What's that? You first apply this theta to H. Apply this theta to H. What will you get? You'll get an automorphism of N. So it's a function from N to itself. So you can evaluate that function at N prime. Is this much clear?
Yes, sir.
So theta of H of N prime, this is an element inside capital N. So you can multiply that with N. So that's what you do in the first coordinate, and in the second coordinate, just multiply those two H's together. Now is it clear?
Yes, sir.
Yes.
Yes, sir.
Okay. Now let's start with some easy examples. Now tell me what happens if I take theta to be the trivial homomorphism. It sends every h to E. Then how does this group operation look like? You start with n times h, n prime, h prime. What will this be? N times
Sir, E
Identity.
identity.
E. Right. So it's not identity. I should be more careful. This E is inside ought n. What's the identity over there?
Identity mapping.
Yeah. The identity inside ought n is just the identity function, identity mapping. So theta of h is the identity function. That identity function will send n prime to
N prime.
right. Is that clear to everybody?
Yes, sir.
Yeah. So theta of h is just the identity function. It will send n prime to n prime. So I'll just get n times n prime in the first coordinate and h times h prime in the second coordinate. So now see what happens. N semidirect product h with theta being the trivial operation. How is it looking like? As a set, it consists of ordered pairs of elements coming from n and h, and the multiplication is component wise. So is there a different name to such a group?
External direct product.
Yeah, this is called the direct product. Then n this h is isomorphic to n cross h, which we saw in the previous lectures. This becomes the usual direct product.
Sir, what is that notation is called between the isomorphic and the left side?
Yeah, I don't know what it's called. I've hardly used this in my research. But whenever such a notation shows up, you can just call it by the command that you give LaTeX to print this. I think it's L times or something. The command for this is \L times, if I'm not wrong. Okay, is this clear? Yeah, is there a doubt?
Yes, clear.
Okay, fine. So this is semi-direct product. So example 1. Now let's start with example 2, which is a non-trivial example. So take h to be z2 and k to be z4. Let's start with 3. Let's take h to be z2 and k to be z3. Take theta to be the function sending h to ought k. Here h is z2, ought k is ought z3. And the function I want to take is the one sending one bar over here to the function I'll get a function over here which sends 1 bar to 2 bar. This is a bit complicated, but is this clear? I'm sending an element in H to a function. Sorry, I shouldn't say K, I should say N. Yeah. I have to start with an element in H and I have to send it to a function from N to itself. So I'm starting with 1 bar in Z2. I'm sending it to the function which sends 1 bar in Z3 to 2 bar in Z3. Is this clear? Is this homomorphism clear?
Yes, sir.
Okay.
Yes, sir.
Then we can construct the semi-direct product N times H. Now tell me, will this be abelian?
Yes, sir.
Okay. So let's see. I want to disagree with you. I want to say this is not abelian. So how? So take this element 1 bar, comma 1 bar and try to multiply this with 1 bar. Sorry. Yeah. Try to do this. Try to multiply these two. What do you get? So again, going back to the definition over here, you first write this 1 bar. This is the n component. Okay. Then instead of just writing this 1 bar, you look at theta of 1 bar, evaluate that at this.
The 2 bar.
Yes. So this will be this times, but I'll write plus 2 bar. Then comma, just multiply the other two, right? So that's 1 bar plus 0 bar. This is just 0 bar comma 1 bar. How about the other way? 1 bar comma 0 bar times 1 bar comma 1 bar. So first write this 1 bar. Then you take theta of this. Now theta is a homomorphism and this is the identity, right? So theta of this should be the identity inside OR 10, which means you'll get the identity isomorphism. That identity isomorphism evaluated at 1 bar will give you 1 bar, right? Then you just add the other two in the second coordinate. What you get is 2 bar comma 1 bar. Is this clear?
So repeat the multiplication between 0 bar and
Yeah. So what I should do is instead of just adding the first two coordinates together, I should take this 1 bar and then I should add that to theta applied to 0 bar, further applied to 1 bar, right? If I go up, You can see that's the definition. You first apply theta to the h coordinate of the first one. That will give you a function from n to n. Evaluate that at the n coordinate of the second one.
Yes, sir.
Here n is this, h is this, n prime is this, h prime is this. So you can see n theta n times theta of h evaluated at n prime here, comma h times h prime over here. Can you see that?
Yes.
Okay.
Yes, sir.
So you saw that the same two elements multiplied in a different order gave you a different answer, right?
Yeah.
So this group is non-abelian. Semi-direct product is a construction which helps you construct non-abelian groups sometimes. Okay, even if you start with two abelian groups, their semi-direct product may not be abelian. And I would like to end today's lecture on the fact that Dn is isomorphic to a semi-direct product of Zn with Z2. Is this okay? Try to wrap your head around this. This Zn is generated by R. This Z2 is generated by S. Okay? This is the normal subgroup. You can denote this by N. This is your N. And this is your H. To give you this semi-direct product, I have to tell you what the homomorphism is, right? Theta is a homomorphism from Z2, or maybe more abstractly, from S to aught of the subgroup generated by R. What this homomorphism does is it takes S and it sends to the function, it sends S to an automorphism which sends lateral R to R inverse. Note that R mapping to R inverse is an automorphism of the subgroup generated by R. One can quickly check this. There's a shortcut way of doing this. This group is abelian, so these powers, you can just check that R going to R inverse is a homomorphism. Otherwise, if your group is not abelian, then it becomes an anti-homomorphism, what it's called. But turns out R going to R inverse is a homomorphism, but it's also bijective, so it's an automorphism. Now let S be mapped to this automorphism. Okay? Let S be mapped to this automorphism. So then, now this will be your homework. Go back, review this entire lecture, and try to see if the relations in Dn between R and S, these are satisfied by this semi-direct product. Okay?
Okay, sir.
You have to do these three checks. The first check is that the order of R comma identity is n. The order of identity comma S is 2. Then You have to check that S inverse is equal to R inverse. So that in this language says E comma S times R comma E times E comma S inverse is equal to R comma E inverse. And just for fun, you can try and show that order of R comma S is 2. Try to do these 4 checks. If you want, you can take a screenshot.
Hello, sir.
Done, sir.
Yeah, okay. Any doubt?
Sir, is there any way through which we can get to know that semi-direct product of two abelian group is abelian without doing
Yes.
calculation?
Yeah. So it turns out this theta is the only obstruction, right? So this theta, if this becomes trivial, if this theta becomes a trivial homomorphism, so it sends everything in H to the identity automorphism, then the semi-direct product becomes abelian, provided that H and N are abelian.
Okay, sir.
This theta measures how H acts on N by conjugation. So this theta tells you how H acts on N by conjugation. Uh, that's the abstraction over here. So if theta is a trivial homomorphism, then it says that H acts trivially on N. And so if you know that N and H are abelian, then the semi-direct product is abelian. Any more questions? Okay, if not, that's all I wanted to say. Thank you
Thank you
for
so much
attending.
for such an engaging and wonderful session, Anand sir. Participants, please note that next session will be on Monday, that is 24th November 2025, from 6 p.m. to 7 p.m. as per the schedule. Let us meet there. Goodbye.
Okay, bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.